Okay, hello and welcome to the final session of MRI Together. It's been a blast the last few days, and I'm sure the fun will only continue in this final session. So I'm Sophie. I'm one of the chairs of the organizing committee, but I'll also be moderating this session. So before we get started, let's just go through a little bit of housekeeping, just so that you all know this presentation is recorded and broadcast live on YouTube, where you can also find closed caption generated automatically if you need that or prefer that. Remember to be aware of the code of conduct that is posted on our website so that everyone can have a good time. And if you have any questions during the presentations, please put them in the Q&A box on the side. General chat, hellos and whatever you can put in the chat box. We're keeping those separate so that we can make sure that we don't miss your questions. But with that, we're going to get started with our first presentation today. We're going to learn about image reconstruction using Julia. And it's going to be given by Jeff Fessler from the University of Michigan and Tobias Knopp from Hamburg University of Technology. And they're going to give it together. So I think we're starting with Jeff. Jeff, the floor is yours.
Okay. Are you going to share thank you very much. I'd really like to thank the organizers for setting this up. All right, good. Looks like you're seeing the talk that I presented now. And I prepared this talk in Julia. Actually, I'm all in on Julia now. There's a nice set of tools for creating documentation that goes with Julia code, and I've used those tools to create this presentation. I put a link to it in the chat so that if you want to follow any of the links that I have embedded into this presentation, you'll be able to do that easily. I'm going to give a little bit of a general overview, give a couple examples, and then hand it off to Toby, who's going to do a deeper dive into the MRI reconstruction aspects. The theme of this workshop is MRI Together, and I'd like to offer a little perspective as an old guy on some history. So back when I was a PhD student in the late 80s, there was a group of mathematicians that started a software sharing service called NetLib, where you email your software as a text file basically to this email address, and then you could request other people's softwares by sending email to that same address and get software. And actually, within the last year of my PhD, I made my first contribution to that open source community, and amazingly, it's still available now. Now you can access it on the web rather than having to send email to a certain address. At that time, it was very much, I would say, kind of lone actors developing code and submitting it to this shared repository. And I think the field has come a long way in terms of the together theme of this workshop. And just as one example of that, if we look at the non-uniform fast Fourier transform that my co-presenter Toby developed, he wrote 99% of the code, but you can see there's 14 contributors to this Julia repository. And I'm sure Toby would agree that the contributions of other members of the community really have strengthened any of the toolboxes or set code packages that are available online. And so I think today, if you're interested in contributing to this community, instead of starting a place, whatever Bay Area Reconstruction Toolbox or Michigan Reconstruction Toolbox, I would really encourage you to join forces with some of the other public repositories that are out there and contribute to them. So I'm focusing on Julia here. And by the way, here's links to some resources for MRI specifically, everything from block simulators to non-uniform fast Fourier transforms to different collections of MRI reconstruction tools. And I think the primary place to go to those is the magnetic resonance imaging organization that Toby will talk more about. So we're both talking about Julia. And so let me just spend a minute talking about why we're focusing on Julia and why I'm all in on Julia. And these first three bullets here are really together the main reason for me. I really care about speed, right? Because we deal with large 3D images or even time series of 3D images. But at the same time, I want the ease of software development. I don't want to write in assembly code or even in CUDA, raw CUDA code, if I can avoid it, to get that speed. And so Julia really solves what people call the two-language problem. My MATLAB toolbox is actually, a lot of it is interfaces to compiled C code that I had to write separately. And that's the two languages, right? The C code for performance and the MATLAB or whatever higher level language using for the interactivity. Julia gives you both of those in one language because it's interactive, because it has dynamic typing and so on, but it's like you experience when you use Python or MATLAB, kind of a command line like experience. But behind the scenes, it's a compiled language using the just-in-time compiling of something called the LLVM compiler. It also, a part of the speed is that it's easy to use threads, much easier than in C code, distributed computing and GPUs. There's a lot of things that also facilitate speed, such as using only the smallest data sizes necessary. For example, in MATLAB, if you want to use a sparse array, it has to be double precision. So that's using 8 bytes per every data point. In Julia, you can have a sparse array of any type, including a 16-bit float, excuse me. When you call a MEX file from MATLAB, it's making a copy of the array, whereas in Julia, everything's called by reference. And so you don't make a lot of unnecessary duplicates. In fact, even if you reshape an array, it's referring to the same underlying data, so you don't duplicate it. And that memory efficiency is really important in data-intensive applications, including MRI reconstruction. In case you don't know, and you've probably used Jupyter notebooks, but the JU in Jupyter stands for Julia, right? PY for Python and R. So it's really a language that has been developed with that kind of interactivity in mind. And then, okay, there's the coding in it as well, and there's a number of features that I like, especially the fact that you can write it with a syntax that really matches the math, even using Unicode characters if you so want. And it's really designed from the ground up for processing numeric data like we have in MRI, whereas NumPy was kind of an add-on to Python, right? It wasn't regionally developed specifically for processing numerical data types. And then, all the libraries that you use to in any high-level language are available as well in Julia, fast Fourier transforms, linear algebra, and so on. And then if you need to call other languages, including reading MATLAB files or even calling MATLAB itself or Python or C, you can do that when you need to do so. But from the point of view of reproducible research, this is where I think Julia really shines. Everything is based on Git. So every single version of a package you develop has a Git commit associated with that, and a Git tag associated with that. And you can distribute code with what's called a manifest that says, for this code, this is exactly what versions I am using of these different packages. And this is very different. I've shared MATLAB code for years in the spirit of reproducibility, but that MATLAB code keeps evolving over time. And if you try to use today's MATLAB version of my toolbox to reproduce a paper that we wrote a decade ago, it may not work so well because of new features we added, or even MATLAB itself adding new functions that conflict with the names of functions that I had in the paper, or the code at some point. So Julia, like Python, has namespace control using commands like using an import to prevent that conflict with set functions of the same name between different languages and ensure reproducibility to a degree I've never seen before in any other language. And of course, by the way, it's free and open source. It's a newer language. It's actually been around for over a decade, but I'd say it's really in the last 4 years that it's been useful. It's version 1.0 that came out in 2018 is really where it began to be, I think, a solid language for doing problems like the ones we're solving in MRI. We've used it since 2017. It was a little rough the first year and taught thousands of students with it. All right, so last time, a year ago, I gave a little bit more of a deeper dive into the Julia language. Here, I'm just going to give a very high-level example just to give you a taste of it. So, for example, if you want to define this simple polynomial function in Julia, here's 3 different ways of doing it. One of these ways looks a lot like the math, right? F of x comma y equals x squared plus y cubed. I challenge you to find any language where you can write such a function in a way that looks as much like the math as this does. And then, of course, you call a function like you would. Here's a little bit more An example a little more related to what we do in MRI image reconstruction. Suppose you wanted to implement gradient descent as a very simple method for image reconstruction or solving some optimization problem. So that's an algorithm where you take the current guess of your image, for example, subtract some step size times the gradient of the cost function, evaluate the current image, that gives you your next image, and you loop that over for a certain number of iterations. Here is a whatever 3-line Julia function that implements a general version of that gradient descent function. So of course it needs a function as an input that computes the gradient. It needs a step size and it needs initial guess. And then the inner loop here, the inner expression is extremely similar to the mathematical expression. So I really think that aids readability and even software development. It's not necessarily the most performant way to do it. So if you really want to speed it up, you do a little bit more in-place operations and things like that. And then the code looks a little bit more involved, but you can start by writing this version that looks a lot like the math and then proceed from there. I have a concrete example here of actually exercising that gradient descent function for solving a simple least squares problem. So the gradient of this least squares problem is given by this expression, and you will see in the code there is the function defining. I hope you're seeing my mouse, by the way. Speak up if you're not. I assume you are. There's a definition of a function that defines the gradient. It looks extremely similar to the math, all right? And then we pass that function into this gradient descent with an appropriate step size that, for those of you who know the math, is the reciprocal of the Lipschitz constant of the gradient of this cost function, with some initial image or initial guess, basically. And after running a lot of iterations, you can verify that this converges to the same thing we would get by using backslash, which is the standard way of solving a least squares problem that's small enough that you can do it non-iteratively. So there's just a few lines to illustrate the expressiveness and the simplicity of Julia. It looks, I like to say they've taken the best of Python and MATLAB syntax and put it together, and I hope this gives you a sense of that. Here's an example of creating and displaying an image. In this example, I've created some X and Y coordinates, and I'm using one of my favorite features of Julia, which is the broadcast feature, which is you can take any function, including the one we defined a few lines above here, that is this polynomial function, and apply it element-wise to its arguments. Of course, in MATLAB, this is built into some functions like cosine and sine, right? But in Julia, any function that you write or exists in the language can be applied element-wise to its arguments. This is called broadcasting, and it really saves you as the developer from writing loops, right? The loop are hidden basically in this dot here. And then after I create the image, I can display it here. So that's a display of that polynomial function. Okay, so there's a little overview of Julia, and I'm almost on time here. So the theme of this session was expanding your image reconstruction toolbox. And when I first saw that theme, I thought it meant for us as software developers, how do we get other people to help us write our toolboxes? But maybe it was for you as users, how to expand your toolkit. I'm not sure which, but in either interpretation, I want to make a comment, which is that I have been somebody, and there are lots of examples out there of what I'll call mega toolboxes, like MERT, the Michigan Image Reconstruction Toolbox, that is a giant collection of a huge number of routines for SPECT, PET, CT, MRI reconstruction of all different varieties. And I think that's not the Julia way. In Julia, we tend to have more specialized toolboxes that people can borrow functions from in a very interoperable way, and then combine them to accomplish some goals. And this has been described a little bit as a more a la carte approach. When I first started switching to Julia, I went in the same way of thinking, oh, I need to write all these functions in Julia, and I created a Julia version of MERT. But over time, I've actually been pulling routines out of that and putting them in more specialized toolboxes that are easier to test and debug than being part of a mega package. Now, I was discussing this difference with somebody recently in a Zoom meeting, and they said, well, a la carte menus are nice if you know what you want, but sometimes it's desirable to have the chef's recommended menu of the day, right? And so I think the way we accomplish that in Julia is by creating examples for you that have documentation that show you how to use these pieces to accomplish certain goals. And I'd like to just spend maybe a couple more minutes illustrating one of those. I had two here, but in the interest of time, I'm going to start with low rank plus sparse dynamic image reconstruction. So I'm going to click on this link, and this takes me to the documentation that goes with a set of examples that I've included. I don't know if you can actually see. Yeah, I don't think you can actually see the URL. You know, I will post that URL in the chat just in case somebody wants to follow along with that separately in their browser. I think the browser is only not showing the header of the browser. Low rank plus sparse, let me scroll down to the code for a second here, was a method pioneered by Ricardo Otazo in the MRI setting, where you want to reconstruct an image as being a sum of a low rank plus and a sparse part. And you do that by solving an optimization problem involving a data fit term where you add the low rank and sparse part, you put it through your MRI encoding matrix, and you try to get to that to match your case-based data. But you include regularizers, one term that has a nuclear norm that encourages the low rank part to be low rank by penalizing the sum of the singular values, and another term that encourages the sparse part to be sparse with respect to a temporal Fourier transform. So you take the temporal Fourier transform of the sparse part, this is dynamic imaging, and then take the one norm of that which encourages sparsity. Now in Otazo's original paper, he used iterative soft thresholding ISTA algorithm, which is a first order method that solves the problem but does so slowly. And my former PhD student, Claire Lynn, investigated a proximal optimized gradient method that converges much faster. She did that in MATLAB, and for this purpose here, I've re-implemented that in Julia to try and reproduce those results. I want to point out that everything I'm showing here actually was written in Julia, and then the Julia comments have in them the markdown that leads to this HTML page that you're looking at here. And I really like, it's kind of like a Jupyter Notebook, but one you can just view in your browser without having to open a separate application to see the Jupyter Notebook. And I'm a very visual learner, so I really like to be able to read in an environment where I see the math, I see the code, and then eventually here we're going to see some images. So in the spirit of this a la carte approach, this example builds on a bunch of tools taken from different toolboxes. So I have a FFT operator that's coming from the Julia version of the Michigan Image Reconstruction Toolbox, as well as a sensitivity encoding operator and so on. I'm taking the FFTs from the FFTW library and so on. And so in Julia, you don't have to specify which functions you're taking from which library. You could just say using MERT, but that would give you access to every function in the library, which is fine, but I find it helpful as an educator at least, and as a future me reading this code later, I'd like to remember which functions came from which library. So if I need to go look on the documentation of those functions or wherever, I know where to go look. So I'm specifying exactly at the start of this, let's call it notebook, which functions from which library are being used. And then I'm actually reading in the exact same data that Claire Lynn used in her paper here using the MATLAB matread function here. This is the final image that the sequence of 40 images that she reconstructed in her code at the time. I'm organizing it in a way that's suitable for what I'm doing here. This is 2D plus time. So this is the X, Y dimensions, number of coils, 12 coils, and 40 time points. I'm just going to give you a high level overview of this notebook, and then if anybody's interested in low rank plus sparse reconstruction, they can go back in and dig into the details more carefully. These are the sampling patterns associated with the 40 time frames. They always collect the center of K-space, and then some random subset of the high frequency K-space lines. This is exactly what was used in Ricardo Otazo's original paper. There's coil sensitivity maps that were provided by Ricardo that we're reading in here and getting ready. There they are for the 12 different coils. We're going to need to do a temporal Fourier transform. So I'm using this FFT operator here telling it the dimensions of the image, and that I want to take a Fourier transform only along the time dimension, which is the third dimension, and I want it to be a unitary Fourier transform, which is the most convenient for a proximal gradient kind of method. And just as a sanity check, here is the temporal Fourier transform applied to the reconstructed image that Claire produced. And sure enough, you can see this is quite sparse. So the idea that it's sparse seems like a reasonable model. We also need an encoding matrix. All right, so that involves sensitivity encoding using the sampling patterns and the sensitivity maps. And it's, if you know about dynamic MRI, that's a block diagonal matrix where you have separate blocks for each of the time frames. So I'm constructing that here. I can't, that's it. It's not, we write it on paper as a matrix, right? In code, it's an operator. It's an operator that has this many rows, this many columns, and it takes a sequence of 40 input images of this size and produces an output that corresponds to the number of time frames, the number of coils, and the number of samples per time frame. And then, okay, there's an extra step here because we're involving both the low rank and sparse. I'm taking a little more time than I'd promised, so at this point I'm just going to say, and then finally we put all this into we get an initial image, we put it into a proximal optimized gradient method somewhere after defining all the proximal operators that we need for that. And so this algorithm right here is the key one. It's a proximal optimized gradient method with what's called restart that makes it even faster. And I've got 3 different versions of it here. The original one that's called Vista, and this really optimized one. And we can look at the reconstructed images and finally look at how fast are these different algorithms can reach reducing the cost function. You can see the optimized one reduces it the fastest. So that's one example of combining tools from different toolboxes, optimizers, sensitivity models, data, and so on to implement a useful reconstruction method based on a low rank plus sparse model. So with that, I will now hand it over to Toby, who's going to dig into MRI reconstruction in a little bit more detail. Thank you. I will stop sharing here.
Okay, try share my screen. So I hope one can see my, can one see my slides now?
Yeah, that looks good.
Okay, perfect. So I'm, yeah, so my name is Toby Knopp, and yeah, I will give the second part of this, yeah, MRI meets Julia, yeah, tutorial or session, and yeah, I want to spend some small words on myself. So I started using Julia in 2012, which was actually the year where Julia was introduced. And before that, or in that time, I was a professional C++ programmer and have used MATLAB and Python a lot. And when I started Julia, I was wondering, well, there's another effort to build something new, but I wondered, why do we need that? Because isn't Python all we need? Because Python at that time was yeah, good enough to do numerical computing. It was open source. It had various toolboxes there. And I wondered, why do we need yet another tool? And Jeff outlined very, very nicely what is kind of the space that is missing when you just look at Python. So what Julia adds on top of that. And I think this was, I tried to prove myself that Julia is not a thing, but when I tried it, I was so convinced that I stick to Julia since 2012. And we are developing 100% of our research software with Julia. Okay, one second comment I want to make is that Julia might look for somebody as a toy language. So it seems to be sold as a language for scientific programming, which it is. But if you look at all these open source tooling that Jeff outlined, you can see that actually Julia is a software or programming language that allows to develop software in a very professional way, which is yeah, which I want to stress here. So this is really not a toy thing, but it's really meant for professional software development. Okay, and with that, I would like to dig into my slides. So yeah, I give this talk here together with Jeff, but actually many people contributed to the package, in particular in the last months. And yeah, I use what you see here is a notebook system. It's not a Jupyter notebook system, but so-called Pluto notebook. It's a little bit different. I will not say too much about Pluto right now, but again, all this material is done with Julia, and you can see here the packages that I have loaded using this a la carte approach. And you can see here, these are more general packages that I load, and these are the MRI specific packages. And yeah, well, now start a little bit with my vision that I had when we developed MRI Reco. And let's start with this first part. So if you look at medical image reconstruction ingredients from a higher perspective, so I'm not just developing MRI, but I'm also in the field of so-called MPI, which is another technology or imaging modality. And I've also done computer tomography research. And then you usually look at these imaging modalities from a higher abstraction way. And you will find that one important ingredient is that you require physical models. And I think we all agree that for MRI, this is, or for each modality, this is completely different. So the physical model of computer tomography is completely different than in MRI. And therefore, we need dedicated code for each imaging modality. But then what do we also see is there is most often some inverse problem being solved. Most often it's linear. Sometimes there are nonlinear components. And at that point, we see, well, that's not so MRI specific. It seems to be a general tool that we are using here. And then we go forward and see in the last 10 years, we have seen much progress in MRI by putting in more prior knowledge into reconstruction, by using, for instance, different sparsity transformations, or in the last 5 years, a lot of machine learning has taken place. And again, the question is, how much is this actually MRI related? And the answer is in parts, yes, but it's also more general. But there's another thing, you also need these computer science things. So you need things like file handling, visualization, and so on. And again, you can see that this is not MRI specific. And this, again, motivates why it makes so much sense to try sharing these things between different imaging modalities. And therefore, if you look at this picture, this is actually a state of the package family that we had 2 years ago. You can see on the left, basically, I have the scanners that we are using in my research group, and there we have some measurement data coming in. Then we have in the middle our package ecosystem in Julia, where we have in orange and in green shared packages, which have which are not MRI or MPI specific. And then on the bottom, you can see the MRI and MPI specific parts. So I try to develop this in a modular way. And then, of course, what comes out is some image reconstruction. But there again, the point is, if you have some reconstructed image, how you post-process it. So there is the entire family of image processing tools that is usually not specific for a certain modality. So it makes sense to split this off. So this is the vision why things are developed like they are, and how I present them in the next next minutes. And with that, I want to show you some, or give you some links of where things happen. So I have to say that the things that we are developing here is not set in stone. So these things are evolving and are moving around, and that things are evolving is actually a good thing, because it means progress is being made. So as always in research, new stuff appears. the packages, get better, new functionality is added, but also sometimes things are restructured when we identify things that are duplicated code and so on. And therefore, it doesn't make sense to freeze the entire state if you want to follow the state-of-the-art software development in magnetic resonance packages. So I picked some so-called GitHub organizations. So organizations are just collections of packages. They are not such a formal structure, but they often want groups packages together. And there you can see that we have, for instance, Julia images, which has nothing to do with MRI. But if you want to do something with your image, which I've shown here, so you want to do image processing, you can just grab one package of Julia images and then you can use that as is, which means that you should not, if you are an image reconstruction person, you don't need to develop the image processing code on your own. And then we have two organizations where we develop now image reconstruction specific packages. The first is Julia Image Recon, and the first is magnetic resonance imaging. I will focus today more on this magnetic resonance imaging organization, and will outline this in more detail. But there's, by the way, also an organization, Julia Neuroscience, where a lot of these neuroscience MRI post-processing is happening, if you're interested in that. Here are just images which showcase kind of how these organizations look like, and in the bottom you can see then the repositories. And by the way, the Julia packages are most often named something.jl to make clear that this is a Julia package. This is a convention being used. And with that, I move on and want to outline just some important packages that I think one should have, one should look at if one is interested in using Julia for image reconstruction, but also for MRI simulation. And I started here with this general section to make clear that if we find functionality that is not MRI specific, then we try to develop it in dedicated packages. And many of these things were already there. So for instance, HDF5 is a file format that is being used in quite a lot of file formats. For instance, the ISMRD file format uses HDF5, and we can just use this package. Then, of course, we have an FFTW package. But now it gets interesting, because now we have this nfft.jl package, and one could have said, well, it's MRI specific. We use gridding. Let's put that into some MRI package. But actually, we did not do that, because we tried to just implement the transformation itself, the non-equidistant fast Fourier transform, and make this independent of MRI. And this outlines quite well why this package is in this general section. Then we have wavelet.jl for wavelet transform. And there again, it was something which I never had to implement, because it was just there. And then I want to focus on two other packages, which are, in my point of view, also very important for future development in the next years. The first is CUDA.jl, which is the go-to package for general graphic processing operations. And the second is Flux.jl, which is a deep learning library, which is, I would say, plays in the same league as PyTorch. So I use that actually to replicate PyTorch examples, and think this is on the same level of maturity, at least for doing such deep learning based MRI reconstruction stuff like we do in MRI research developments. And then it gets interesting. Now we move over to the more imaging specific packages. I enjoyed using the so-called image phantoms package, which has various nice packages like the Shablogan phantom. And this again shows it doesn't make sense to implement Shablogan in an MRI package or in a CT package. Just put it into image phantom, and there the fandoms are. So this is again the strengths. Then of course we have MERD. We have already heard about that. We have the package called regularized least squares, but there's also other packages like nifty.jl and dicom.jl, which I don't develop. I just use them. And with that, we now come to the core of what I want to present today, and these are of course the MRI specific packages. And I will not go through all of them, but you can see that quite recently we tried to separate a lot of core functionality into dedicated packages, so that we don't have this large, huge package, but have smaller individual packages. And I just wanted to make one point of a package which is called BART.io, which was recently developed in the last months by Jakob Asländer and Aurélien Trottier, which allows to call BART function. And I was actually thrilled about this a lot, because I will later show you comparisons where we use BART and MRI-RECO, and this package allowed me to actually use functionality from both packages together, which was quite useful to me. And then you can see we have dedicated packages for MRI field maps, for fingerprinting. We have an advanced simulation package called ComMRI. And then we have later on a lot of things which are kind of now part of MRI-RECO. I will come to this. I sketched this here with some hand drawing. Sorry for my bad hand drawing, but this was the easiest way to draw it. And what you can see here basically is the package hierarchy. Because we don't develop packages in a flat manner, but we try to make them or look at the dependencies. Because if you look at MRI-RECO, of course, an MRI reconstruction package requires some operators, MRI operators package, which is there for setting up the operators. And then we require these linear solvers or iterative solvers, which in our case are in regularized least squares package. And this also outlines quite nicely that it depends on yourself where you want to start. So I like the example that we have seen before by Jeff, where you have seen that the operator itself was built up step by step, and then we just put it into an iterative solver. And I think if you are a developer of reconstruction software, this is the correct interface. So this is what you want. However, if you are more of an MRI reconstruction end user and don't want to build up the operator itself, you need kind of want to simplify this code. And this is where MRI-RECO comes in, because MRI-RECO tries to automatically build up these operators together. And I will now scroll a little bit forward to come to some interesting things. So if we now look at the features that we have in these later sub packages of which are connected to MRI-RECO. So if we start here, this pause here, we can see that we have file handling support. Right now we support Bruker files and ISMM-RD files, not more, but potentially if there is interested in, we might also be able to implement Siemens or Philips or whatsoever file format if there's interested in, and people supporting us in developing this. Then the most important thing, I think, is this lazy setup of imaging operators. And there we have several things. We, of course, support non-equidistant 2D and 3D trajectories, field map correction, parallel imaging, subsampling, and also have some experimental low-rank code. So I think this is nowadays pretty standard. But it's nice to have all this in one library. but you are not limited to that, because if you have one sub operator, let's call it like that, it's quite easy to build a higher or a custom one or some specific imaging operator that looks a little bit different. So it's not like that you have just fixed operators, but you can change them on your own. So this is quite easy. Okay, we have iterator solvers. We are type agnostic, so you can use float 32, float 64. Actually, I think we could also support other floating point numbers, but these are the most common ones. And yeah, we aim to have our package to be hackable. And what helps a lot, I think, in understanding the flow that we have in MRI Reco, and when I tell now MRI Reco, I usually do not just mean the specific package, but more of the family. And then you can see that we usually start with raw data, and this raw data comes from files, and these files are stored in something which we call a raw acquisition data object. So, and this is a higher order data structure. In C++ or Python, you would call this a class. We call this a struct. And it contains all the information that you require to store data into a file and retrieve it. So this is the idea there. And commonly, this raw acquisition data object is not in a form that you can directly use it for reconstruction. So for reconstruction, you want to often change dimensions and so on, and therefore you can bring this raw acquisition data object to, or convert it into something which we call an acquisition data object. And this is now the data ready to go for reconstruction, basically. And this data that you have seen here, this acquisition data object, can not only be obtained from raw data, so measured MRI data, but you can also, we have a small simulation package called MPI simulation, where you can also simulate this data, including field map and parallel imaging and so on. So everything there is in place. It's not a complicated block simulator, but a very simple from the common MRI imaging equation. Then we have this reconstruction function, where I said this is basically code which brings together, so you are setting parameters, and the green box tries to then figure out which reconstruction you want and then apply it. But again, I want to emphasize this, that you can use the upper boxes here and then say, well, I want some custom iterative solver. And then you can just exchange the green part with whatever you like. So we are not restricted. You are not in such a lock-in thing here, but you can mix things together here. And then we are in this blue area where we have the image data, and there we usually don't want to provide packages, but there you can simply use the packages which are there in Julia. Okay, and now I need to also speed a little bit up. I want to give you at least one example where I showcase to you how commonly an example looks like. So you can see here that we are loading MRI Reco. And then we have here the file handling. So we say, well, this is a file that we obtained from a Bruker scanner. So Bruker, by the way, is an MRI vendor for small imaging systems. And then you load the data with this call to raw acquisition data, and afterwards we convert it to this acquisition data object. Then we come to these 3 lines where we prepare the reconstruction, where you can here then enter reconstruction parameters. You don't need to use this specific interface using a dictionary, but we like to use it because you can serialize these parameters. This means if you quite often, if you are doing lots of reconstructions, you often want to serialize them into some text file, and these parameters here can very easily serialize to text files, and then the reconstruction routine itself is basically just a black box. So you call reconstruction with the data and your params. and that's it. And then you obtain iReco, which is the image that you then can save into a nifty file in this case, or can also to a DICOM file, however you want. And yeah, these 10 lines are then here in this Pluto notebook, yeah, outlined here. And just to want to make one point here clear, if you look at this raw acquisition data object that I loaded here, you can see here that within raw we have this raw.params, and if you open that, you obtain all the information that was inside the acquisition file. So, for instance, this was measured with an ICANN 1 Fessler system in Lübeck. The sequence was T2 rar. We had all these parameters and so on. And this is quite useful if you want to explore data. This is very, very nice. And in raw.profiles are the common profiles, profile information. So this is the actual data. And if you now find all these namings here complicated, I have to say that we actually did not invent all these names, but we used exactly the same elements that are within the ISMRD file format. And so this is really one-to-one. So this is nothing we invented, but it's the ISMRD files have proven to be a good container file, and when we just replicated that, which turned out to be quite effective. Okay, yeah, then we performed the reconstruction as I outlined before, and if you now look at the results, so this is an animal model that we imaged here, and the point now is here, the upper one is the one that we reconstructed with imge-reco.jl, and the lower one here, this here one, is the one that was contained or that came with the scanner. So the scanner had a reconstructed image itself, and this came with the scanner, and then we can compare and see that it looks quite similar. You can also see that the resolution is a little bit different, but yeah, you get the idea that everything is very, very accessible. Okay, I skip conversion. I skip also the simulation part because I actually want to give or talk a little bit about MRI-Reco benchmarks. So MRI-Reco benchmarks is a recent effort where we try to compare different reconstruction packages. And in particular, we try to compare MRI-Reco.jl and BART. And when I say benchmark, I do not just mean the performance in terms of time, but also in terms of accuracy. So we actually wanted to look whether we can get the same reconstruction result. And the idea was, of course, born from this ISMM reproducibility challenge, which we also participated in. And there you can see here just an example from our paper that if you do this is a sense reconstruction, and if you do the BART reconstruction and the MRI-Reco reconstruction, they look very, very similar. And that they look so similar is actually so a very good thing, because it means that both our libraries implement the same mathematics, which is not so clear and not so simple how it sounds like. So if we write something in our paper and how we implement it, that even if we want to try to write this or to match this, we often have implementation details that we are not aware of. So the key thing here is, if we have different libraries and can compare them together and make them generate the same images, we absolutely get a better understanding. And in that spirit, I want to also emphasize that this is not a BART versus MRI-Reco thingy, but it's more, let's bring these together and highlight that they can produce the same things. And now I come to the benchmark results, and there I have to say, when we started, BART was something like, I don't know, 20 20 times faster. So this was something where we sat down then and tried to optimize a lot. So nowadays, with a lot of these optimization that we put into it, you can see that this on the x-axis, you can see the number of threads that we put in. We have in blue 2 different possibilities. So there is either the possibility of using something which is called the tuplets optimization, or there's a non-tuplets variant where you use the gridding operators directly. And you can see that the MRI Reco parts, it's in light blue and orange, are right now faster than BART, and this independent of the reduction factor here. So we have 2 reduction factors. Of course, the reduction factor 4 is more interesting. We also did this for compress sensing, where we are now also faster. But I want to highlight one thing here, because if you look at the result here, I zoom in a little bit, you can see this is the original image. There we have BART, and there we have MRI Reco, where right now you can see that MRI Reco is still worse. And I show this on purpose, not to say that MRI Reco is bad, but the reason is that the mathematical formulation between BART and MRI Reco is right now a little bit different. And we are right now still figuring out how to bring this together so that the regularization parameter can be chosen in the same way. So I want to highlight this, that this is kind of where we have an accuracy issue, and we document it here to showcase, well, there we need to align the implementations. And last example that I wanted to show is eSpirit. So when we started eSpirit, it was super slow. And then we had a collaboration in particular with Jakob Asländer, and we also got various important hints from Martin Uecker, performance hints with some bad things that we did. And nowadays, our eSpirit implementation is really, really fast, and we are somewhat proud of that result. So it was really, really slow at some points, and then we were able to accelerate. And again, I want to emphasize this, that because we did develop this in the open, this progress was actually possible. Okay, I will skip the NFFT example. But NFFT was also optimized quite drastically in the last year, and we'll try to finish my talk with that. So I hope I made clear that Julia can be fast. It is very accessible. One can easily extend the packages. And I want to invite you, if you want more, we have in mrireco.jl, we have a forum. So here, if you press on discussions, you come to the forum here, and you can just ask questions, and probably so we try to answer this. And if you want to join the development, this is a forum. We started to have monthly community calls in Zoom, and you can see here we have this MRI Reco community meetings where we try to meet monthly in a Zoom meeting and discuss the future or discuss development issues. And you are of course invited to join there. And with that, I am at the end of my talk. I will stop my presentation. And thank you a lot for having me and listening to the talk. Thanks.
Thank you both. That was really, really interesting. I'm definitely even more curious to try out Julia after this. I don't think we have any questions that have been put in the Q&A box yet, so I'm happy to start with a burning question that I have, which is kind of to both of you actually, because Jeff, you were mentioning that you'd translated some MATLAB code to Julia. So I wanted to ask about the reproducibility effort there, and similarly, Tobias, you were mentioning it with benchmarking against BART, yeah, you were able to build the same pipeline and you were able to kind of replicate the method, but how much, how do we know, or like that the actual results are exactly the same, or are they just equivalent, and does it matter?
Well, one of the packages that Toby mentioned is this MRI field maps, which is translation of some code from MATLAB to Julia that I did recently. And in the process, I was uncovering bugs in my former students' code. So, and I think part of the reason I uncovered those is that, as Toby hinted at, the Julia, because it's all based on Git, and there's this continuous integration process where I write as many lines of test code as I write of the actual code that you're going to use as a user, or that I'm going to use as a user, right? Just about as many. And I uncover so many bugs, and I strive for what's called 100% code coverage, right? The tools in the cloud will tell you what percent of your code you've actually tested. Doesn't mean it's right, but you've at least exercised it. And you don't know how many times I have said, oh, it's 90%, it's probably good. And then I write a test script for that last 10%, and sure enough, there's a bug in it, right? And so you've opened a can of worms with your question, because in some cases, I don't want to 100% reproduce what was in the MATLAB code because there were errors in the MATLAB code, right? So in fact, I discovered that my student had omitted a factor of pi, and so all the errors reported in our field map paper are actually pi times better than what we reported, right? So the plot shows like 5% error, and it's really only like 1 point whatever percent error. So, so it's not a simple answer to your question, but I am striving to be able to reproduce what we intended to do, even if it's not exactly what we did the first time. And that MATLAB code, by the way, didn't have that same suite of test routines that we very religiously, I think, those of us who are serious about developing packages that other people are going to use are very religious about trying to really provide those test routines, both for the community and for our future selves using the same functions.
Yeah, that's amazing. And I think that's a good example of, how we as a community can strive for reproducibility, but it's hard when we realize that the thing that needs to be reproduced maybe isn't always exactly what you want. Tobias, do you have anything to add to that in terms of reproducibility between old code and Julia?
I think well, I think it's the question you raised is not so Julia related, because I mean reproducibility in research is actually a big thing. But if you see kind of or if you're developing open source software, you're kind of committed by doing things in an accessible way. And one has to say that this is huge effort. So it's time that you spend on not writing a paper, but I've found that it is well spent. So I've also found so much bugs in code that where I've published papers on, and therefore I think in particular I want to make a point that if you just want to publish one paper and then are done and are happy because it landed somewhere, I think that's okay. But the point is, if you want to say, if you build upon that, and that's the actual idea of research, that you reuse that again and again, I think starting from that point of on, one should really make things reproducible. And there's now two ideas. Either you say you need two independent people of implementing that. That could be, for instance, somebody building something in Python and I do it in Julia. I think in that spirit, the MRI reproducibility challenge is actually a very good thing. But there's another idea, and that's if you say we stick all to Julia or to whatever tool, then you need to write tests. And these tests need to be developed not by a single person, but by different ones. And I want to add there that when I started Reco, we were the only users. But in the last year, several new users came to us. And usually they came to us and said, well, Tobias, I tried that and got that error message. Or I got that weird image. And this is actually a good thing, because different users were stress testing our software, and this made us allowed us to write new tests to make things more mature. And I think in that spirit, reproducibility is something which is very, very important in research, in particular if you look at the long-term perspective of using 20 years old papers and still wanting to know whether they are correct or not.
Yeah, thank you very much. We have a couple of questions from Niku in the Q&A box, and let's start with the top one. I assume this is for both of you. It's quite a general one. What has been your favorite bug and any tips for discovering them?
No bugs are favorites, but in terms of tips, one thing I really like about Julia is there's a package called Unitful that lets you create arrays that have units. And so I'm trying to make as much of my, and the way that works is if you think about how data is stored, right? You know, the numbers are stored in a file, but there's sequentially in memory, but there's a header that points to, it says, what's the dimensions and so on. You can include in that header something about the units of that data. And so I'm working hard to try to make as many of my tools in Julia support unitful arrays as possible. And I have uncovered bugs in the process of doing that, because you find yourself adding to things that have incompatible units, and you'll get an error message then from the unitful underlying code. Whereas if you just had numbers and you added them and they have incompatible units, they'll just get added, right? And so that's one tip that I would add there that I think might be unique to Julia, actually, that ability to support unitful arrays. I'll just leave it at that for the moment.
Yeah, so I actually have one favorite bug, which is quite interesting and showcases probably also some downsides of Julia, because quite recently, or 2 months ago, we had something which is called performance bug, which is not so obvious. So in Julia, as we have seen, can be really bare metal fast, but there are something which is called type instabilities, which kind of leads to slow code. But it's not so easy to see it, especially for somebody coming new into Julia. And we had the issue that I was coding around in imge reco, developed some new functionality, and actually introduced some of these type instabilities and made some important code super slow. And what happened then was that I rerun the benchmarks from imge reco, and then I saw, well, we are off by a factor of 10, very bad. And this was actually, again, this point where I said, okay, good that we have these tools. We actually need continuous integration for performance. We don't have that yet, but this is something where I figured out it's important to run code and have examples that are easy to set up to find something like that. So yeah, bug hunting is an important thing in open source development.
Yeah, thank you very much. And for anyone that missed the session earlier today, if you're further east than me, or yesterday, that we had a session on scientific software engineering, where continuous integration, version control, testing, etc. were discussed in some detail. So I highly recommend any attendees that missed that session to go and see that. But in the interest of time, I think we'll skip Niku's other question. You can reply to her in the comments, and we'll move on to our second speaker, Arjun Desai, who will talk about simplifying deep learning interfaces for medical image reconstruction from data to deployment, which, yeah, to me is very interesting. I think I look forward to hearing this talk, because going from case base all the way to clinical usage is so important. So yeah, the floor is yours, Arjun. Oh, sorry, we've lost your sound now. You might just have to turn off and on your microphone. Can't hear you. On the bottom of the screen, there is the little settings gear symbol that you might.
But now?
Yes, now we can hear you.
Awesome.
Great.
Perfect. Awesome. Well, thanks so much, Sophie. I'm really excited to be here, and thanks to all the organizers for inviting me. I think one kind of big passion of mine over my PhD is kind of bringing deep learning tools into practice. And so I'm really excited to talk about how we can simplify deep learning interfaces for medical image reconstruction, in particular focusing on MRI. So the first kind of maybe 5-10 minutes of this presentation will be kind of some slides to go over some where we are today kind of as a community and what are some things that we can do better. And the kind of the more interesting part will be focused on like a hands-on interactive collab notebooks. This is a Jupyter notebook hosted by Google that anyone can run on their browser. So I'll drop the link in the chat. And feel free to kind of follow along as we go through it together. And we'll be using a data set that takes a little bit of time to download. So if you open up the link and just start downloading running the first cell or downloading the data set, we'll be ready to run with it just as soon as we're done with this presentation. So over the past few years, there's been kind of a large push towards open sourcing data in our community. And this has been very exciting because it's allowed us to really open a lot of doors for applications in deep learning, in particular in image reconstruction. So with kind of the growth of open source data, we've seen a bunch of new methods that focus on kind of applications of deep learning and reconstruction and also image analysis. We've been able to even validate a lot of these methods at scale, which previously we haven't been able to do. And so this really begs the question is that because deep learning has become so pervasive in our community, what do we need to do to build the right set of tools so that users can interface, develop, and use the models that we build very, very easily? So in order to answer this question—
Sorry, Arjun. Just to, sorry to interrupt. If you're intending to share your screen and some slides, we're not seeing that at the moment. You're talking so well that I wasn't sure if you were intending to use slides.
I appreciate that. Thank you. I think wasn't sharing. Great. Is it visible now?
Yes.
All right. Awesome. Great. So the first few slides are kind of more boilerplate than anything, but it really, I just want to emphasize that we've done a great job as a community towards pushing towards more open source data. And really, we've been focusing on this a lot for the reconstruction task in particular. And so kind of as we start to think about how do we build the right set of tools for making deep learning kind of hands-on for a lot of our users, we need to really start thinking about what our ecosystems for developing these deep learning methods really look like. So we often have some kind of data that we need to manage or wrangle in some way. So this is data that we may have collected or publicly available data sets that we intend to use. And then we get to the meat of the problem, which is how do we build our models? So there's a lot of work here in things like experimentation, testing different kinds of baselines, tuning different kinds of hyperparameters, which are all part of how we build the deep learning models for kind of the objects or areas of interest. And I think one lofty goal kind of in the spirit of MRI Together is really we want to be able to share the models and the methods that we build quite ubiquitously. So this is not just with our collaborators, but hopefully at some point with the broader community and even beyond. And we need to make sure that this process is very simplified because we don't want to spend too much time in actually sharing the model because that should not be the bottleneck for sharing. So if we're taking a look at data, as I mentioned before, we've done a great job of pushing towards open source data sets. But when we're looking at kind of the publicly available data out there, there's a lot of work that still needs to be done in the tooling that we have for wrangling with the data, especially for deep learning environments. So there's been a lot of work in things like developing good file formats like the ISMRM RD. There's a lot of tools for kind of ingesting that kind of data. But when we're thinking about deep learning, there's a lot of work that needs to go into the infrastructure of optimization so we're not bottlenecked by how we interact with our data. I think another big problem just generally in medical imaging is that the data sets tend to be quite large. And this is great, right? When we're thinking about deep learning data, we want large troves of the data that we have. But when we're thinking about accessibility to the data, for folks that have limited compute or resources or in compute limited regimes, we want to still be able to deliver the data sets to them in some way. So maybe this means making a mini version of the data set that people can use to play around with or for educational purposes. But this is critical for really getting users onboarded onto the data that we have. Additionally, when we're thinking about model building, we've, again, pushed a lot towards open source code, and this has been quite exciting, but it's often led to a lot of fragmented code. So there may be a lot of different code bases that build kind of different things in different ways. And Jeff and Tobias mentioned that there's just kind of having so many kind of different pieces kind of can often also make reproducibility and standardization challenging because there ends up being a lot of duplication or boilerplate code that you need to write. So this push towards open source software is really how do we build good sets of tools that can really be repurposed by other folks in our community. And I think while we're pushing towards this model sharing aspect, and there's been a lot of folks that have kind of been open sourcing their code and hosting their models, or at least like shipping the weights that we use for the models, there are strict infrastructure limitations for how we share our models. So really managing a hub for sharing is pretty difficult. And as a result, it's quite complicated to get set up on local machines, or it's even really complicated to start using the models that people have built. Right? So I have to find the right set of links. I have to download the right libraries in order to get these models kind of up and running. And as a result, it's not really been a first-class citizen in the tools that we've been building, right? So there's limited code integration for this concept of model sharing, but it'd be really great if folks can actually start using the models that we built. So to this end, we've built meddlr, which is a Python package for really taking kind of deep learning from the experimentation stage all the way to the model sharing stage. And while I'll be talking and focusing on the medical image or MR reconstruction side here, it's really meant to kind of tackle the general medical imaging landscape. So other analysis tasks like image segmentation or classification and detection and so on. So some features of meddlr include kind of simplifying how we manage different data sets, as well as curate the data sets that or curate kind of deep learning specific data sets from data that we've collected. It also supports how we can kind of code or build on flexible APIs without having to write a lot of boilerplate code. So this really reduces the amount of duplication that we have when we're thinking about what kinds of code that we want to end up shipping to different users. And kind of one of the things that I'm most excited about to talk about is how meddlr has really enabled model sharing and made it a first-class citizen in this library. So you can go ahead and train your models, have your experiment files, things like that, but it's very easy to go ahead and share the models and build the links and host them in kind of pretty strict and shareable ways. So like standard Python libraries, it's pip installable, so you can install it in any virtual environment or directly onto your system. And when we're really kind of breaking down the meddlr stack, it's important to kind of think about what these different pieces of meddlr really enable us to do. So meddlr is built on top of PyTorch, and it provides a lot of low-level operations for fast Pythonic interfacing with medical imaging data. So it uses a lot of other libraries under the hood, like SigPy or ISMRMRD. So it's definitely not reinventing the wheel, but it does this in a deep learning optimized format, so we can kind of get fast data I/O. We have support for complex valued operations and MR-specific forward operators like sense models and things like that. And then on top of these low-level ops, we can really have structured APIs that allow users to kind of build their own models and data sets and interact with the data in their particular ways. So meddlr has a bunch of built-in models and metrics and kind of compatibility with publicly available data sets like fast MRI or MRI data and skm-tea. But users can also easily extend these for their particular areas of interest. And because the APIs are pretty flexible, it's very easy to go ahead and build custom training pipelines and harnesses. And I think the big part here is that we don't want to reinvent the wheel of kind of all the work that's being done by a lot of the other libraries, but really it brings kind of customization to the forefront for making users be able to train their models quite easily. And as a result of that, we can also share our models using kind of a hub and different kinds of hubs that exist. So again, we're not reinventing the sharing platform, but we're allowing users to take the models that they have, package them in a way that can be easily shared on different platforms, either through standard URLs, so you can host them on Google Cloud or on your website, or on more structured sharing platforms like Hugging Face, which I'll dive into a little bit later. So kind of in this demo or walkthrough, we'll really look at how we can tackle MRI reconstruction with meddlr, and we'll be focusing on using the skm-tea dataset or a mini version of the skm-tea dataset. So we'll be using a lot of dataset utilities that we built with meddlr and the skm-tea package, and think about how we can wrangle the skm-tea dataset with those utilities. We'll dive into customizing training and evaluation for workflows with meddlr. And finally, we'll really just get around to training our own reconstruction model and publicly sharing this on Hugging Face. So if you'd like to follow along, you can kind of jump onto the link that we have put in the chat, or scan this QR code as we follow along. And as I mentioned before, there's some data set kind of setup that'll take some time. So go ahead and start running that. But in the meantime, I'll just give a brief overview of this particular data set that we'll be talking about today, which is the skm-tea data set. And what skm-tea stands for is the Stanford knee MRI with multitask evaluation data set. So this data set consists of 155 clinically acquired quantitative double echo steady state, or QDES scans. And they consist of about 25,000 sagittal slices, so about 160 slices per scan. And what's interesting about this data set is that in addition to kind of the standard raw case-based data, it's also accompanied with a lot of data for downstream image analysis. So it has segmentation labels for 4 different tissues for articular cartilage and the meniscus. And then it also has bounding boxes for 16 different pathologies that were present in the scans. And additionally, the quantitative double echo steady state sequence allows us to analytically estimate T2 parameter maps. And these have been shown to be kind of or at least clinically relevant or useful for diagnostic and prognostic indicators for knee health. So what this allows us to do is we can actually build evaluation metrics outside of SSIM and PSNR, which we typically use for measuring image reconstruction quality, and look at some of these biomarkers that may have potential clinical relevance in the future as are kind of the metrics of interest. And one important note, I think this is some great work done by Efrat Shimron at Berkeley, kind of looking at what are the differences when you train with raw case-based data versus kind of DICOM process data. And so building on top of that, we have these 2 different tracks where you can start with the raw data and go all the way from reconstruction to downstream image analysis like segmentation, classification, and detection. But we also have the DICOM track where if you only want to do image analysis, you can just go ahead and use the DICOMs as well. But for today, we're really focusing on reconstruction, so we'll be looking at the raw data track. And of course, I think it would be moot of me not to mention that we really want to make sure that we're open sourcing the benchmarks that we have and the evaluation protocols that we're building. So we've built the skm-tea package on top of meddlr, and we'll be looking at how to use that today as well. So with that, let's jump into the Colab notebook. So when you open the notebook, there's a bunch of text that kind of goes over what are the different cells and what are we doing at each step. And I'll try to summarize them throughout this presentation as well. So the first step is downloading the data set. So the skm-tea data set is 1.8 terabytes large. So there's no way that we will be downloading that on this Colab environment. So what we've done is we've made a mini version of the skm-tea dataset, which consists of 1 scan in the training dataset, 1 scan in the validation dataset, and 1 scan in the testing dataset. And this is about 15 gigabytes for the raw dataset track. So it takes a little bit of time to download, but what it allows us to do is really deliver a small packaged version of skm-tea that lets people or users actually interact with this data in more of a tractable way. So what we've done is we've gone ahead and downloaded this data set. I won't rerun this, or else it'll take a little bit of time. And then what we're going to do is we're going to go ahead and install the 2 pip packages. So we'll install meddlr, and this is a release candidate version. That's why we're specifying a version. But in the next couple days, you won't have to specify this. And then we'll also install the skm-tea package, which, as I mentioned, is built on top of meddlr, but provides a lot of utilities for the skm-tea dataset. And one thing that we'll kind of jump into later, I mentioned a little bit earlier, is this Hugging Face library or framework. So Hugging Face is a company that has simplified kind of the sharing hub platform for a lot of deep learning models, and they implement their own models and have done a great job of open sourcing very exciting models and different applications of deep learning. And so we'll go ahead and install their package as well, because what we'll do later in this talk is show how we can take meddlr and directly upload our models on Hugging Face for user use. And if there are questions or things, I'll be monitoring the chat, but feel free to interrupt me as well. I want to make sure that everyone's kind of jumping and able to understand what's going on these different pieces. So as just with standard kind of Python syntax, we're going to go ahead and import some libraries that are quite useful. So I'll just go ahead and do that. And none of the setup is a lot of the setup is pretty much boilerplate, but it's just a lot of importing a lot of the libraries that we're interested in using downline. So once this import finishes, what we'll jump into is using the skm-tea package in order to build the data set. So while the data set ships in kind of a deep learning optimized format, there's a lot of additional metadata that we want to extract and store in a particular way so that it's even faster when we're doing our data loading for deep learning. So these don't ship with the data directly, but we offer utilities to directly build this data. So we have this small function that we've written that allows us to fetch the scans that we want to fetch. So we'll fetch it from the skm-tea version 1 data set, and we'll be fetching a particular split. So the splits are either train, validation, or testing. And we have some utility functions for kind of doing things like retrospective undersampling. So we'll be using the Poisson disk undersampling pattern. And then we'll have a data transform that we use in order to format our data in the right way to be ingested into our models. So again, all of these utilities are provided by skm-tea, and you can directly copy this particular function or customize it for your particular application. So as we run this, we can see that like the different training data sets, validation, and testing splits are all being built. And what exactly is being built here are the statistics for the different scans in each of the splits. So what these statistics include are volumetric kind of mean or max, minimum value, standard deviation, things that we often need to use in order to normalize our images prior to passing them through our deep learning model. So there's often a lot of pre-processing that we have to do in order to make sure our deep learning models are training most optimally. So because the data set, this particular mini version is pretty small, we can go ahead and build these stats directly. And what we've also done is pre-computed some masks that we're going to use for training. So the reason that this is important is given the size or kind of the size of the KY-KX plane for the skm-tea data set, which is 512 by 160, Poisson disk, kind of creating a Poisson disk mask can actually take quite a lot of time. So we run this pre-computation for these masks under the hood, and we sample from these sets of masks when we're doing our training. Of course, you can turn this off if you would like, but it would reduce kind of the performance at train time. So let's go ahead and visualize what one example in our training data set would look like. So here, the example that's returned is going to be a dictionary, and it's going to consist of the undersampled case space, the sensitivity maps, as well as the ground truth reference. And we can go ahead and visualize what these look like,
Arjun,
and we can.
sorry, I'm interrupting you again. Would you mind just increasing the text size on
Oh,
the
sure.
browser?
Yes.
We had a request.
Definitely.
There we go. That should be better. Thank you very much.
Perfect. Great. Yeah. So as we can see, these kind of the case space is undersampled, which if we normalize the case space, we'd also see. And the sensitivity maps and targets look kind of as expected. So as each example that's in this training data set is just returned as a dictionary that we'll process later when we're training our model. So in addition to doing our training and having our data set well formatted, we also want to make sure that we're evaluating our methods in kind of a standardized way. And what I mean by this is that when we look at the different implementations of metrics out there, even small changes in how we do our computation can actually cause vastly different metrics or values that we get for the different metrics that we have. So for example, for PS, what we've done here is that we've created these kind of standardized metric classes for different kinds of metrics of interest, especially in the reconstruction space. And it allows us to kind of build custom metrics in a standardized or reproducible way. So we'll just use a set of metrics here, which include PSNR as well as complex valued PSNR. So all these images are complex valued 164. So float 32 for each for real and imaginary components. And then we'll also look at SSIM, MSE, as well as complex MSE. And all of these metrics are built in, but users can also customize their own metrics. So if you want to extend the metric class that we have and build your own metrics and also hopefully include that back in meddlr, that'd be great. And that's what we've been doing quite recently. So Phil Adamson, who's a PhD student at Stanford, has worked on some metrics for kind of visual quality, matching visual quality better than SSIM or other image reconstruction metrics that we have. And we've incorporated some of those into meddlr as well. And so once we've built our metrics, we can go ahead and stuff them into this evaluator class, which we can extend from the recon evaluator. So this is a class that's provided by meddlr. And we can establish what are the different kinds of metrics that we want to build on what different kinds of scales. And what I mean by this is that we can either compute metrics on a per slice scale, or we can do it over the entire volumetric scan. And these actually can cause quite different performance measures. So it's important that when we're reporting these numbers, et cetera, we want to make sure that we report kind of how we computed these metrics as well. But we can see that just with 2 lines of code, we can just take the metrics that we built here and kind of set them so that we can run kind of both slice-wise as well as scan-wise evaluation. So now that we have the evaluator and the data set up, we can also take a look at the different kinds of models that meddlr has to offer. So meddlr has a bunch of built-in models that are often used in the deep learning space for image reconstruction. And what we've done is we've put this into a registry of models that can easily be visualized. So here we're looking at the meddlr or meta architecture registry. And you can see that we have a compressed sensing model with L1 wavelet regularization. So this isn't actually a deep learning model, but it still falls into this framework of different kind of reconstruction modules that we want to use during training potentially. We may also have a denoising model. We have a UNet model, which is a popular feed-forward CNN that kind of is used as different blocks in the reconstruction pipeline. We also offer kind of models that are specialized, right? So a lot of these are architectures, but a lot of new methods that have come out over the past few years have used these architectures and built new kinds of models on top of it, right? So different training paradigms, or how do you interface with multiple models simultaneously? So SSDU is one of the popular self-supervised methods for image reconstruction. So we have an implementation of that in our in meddlr as well as some recent work that we've been working on for how do we do kind of joint image reconstruction and denoising, as well as how do we use augmentations in a self-supervised way in order to perform reconstruction. So noise to recon and vortex are also both models that are publicly available on meddlr. So really kind of the point here is that while meddlr has a bunch of these built-in models, what I expect and would be very excited about are a lot of users who want to extend the different kinds of models that are here or use these models as baselines. And so meddlr really kind of packages these different models well, and you can run your own baselines on top of them, or you can also extend or build your own torch NN modules and register them directly into this meddlr interface. So once we have kind of our, once we have a list of the different kinds of models that are available, we can put this all together in our training harness. So meddlr offers a default trainer, which does all of the wiring for the data sets, the training, validation, testing data sets, as well as building the model, hooking up the evaluators, and actually running the training. So we can take a look at the default trainer class on GitHub, but there's really 5 main methods that you would need to override for your particular setup. So if you have a custom data set, you'd want to kind of override the build training data loader and the build testing data loader methods. And then if you have a custom loss function that you'd want to use, you can also override the loss. So that's what we've done here. Because we're using the skm-tea data set, and I wanted to show kind of how exactly this overriding process would look like, we can go ahead and build the data set using that skm-tea function that we had before. We pass this data set into our data loader, and we pass a lot of the arguments that we're interested in kind of instantiating this data loader with. So things like the batch size, if we're shuffling, things like that. So what you may notice here is that we have this concept of a config, which I'll jump into in just a second. But this config is really a kind of an object that manages the different hyperparameters or setup kind of quality for the experiment. And the reason this is very important is when we're thinking about reproducibility, it's very useful to have some configuration file that tells other users, oh, this is how this particular experiment was run. So I'll talk about that in just a second, and we'll really dive into seeing kind of what this configuration file can look like. So in addition to the training data loader, we're also overriding the testing data loader, which is also used for validation. And we also wanted to build a custom loss function. So we're going to go ahead and specify a particular loss function that we want to use. We're going to use the MAE implementation in meddlr to just go ahead and run the run this function on the prediction and the target images. And so this will allow us in a reproducible way to get the numbers or kind of the MAE of interest. We set this to the loss, and we go ahead and return that function that computes the loss function. And of course, because this is a custom data set and we're kind of showing how we want to build this evaluator, we have this skm-tea evaluator that we created earlier, and we can instantiate that with our config, as well as kind of what the particular data set name is. And the reason that this is important is that the data set that you may be using at evaluation may potentially be different, right? So you may be using the validation data set when you're building an evaluator for validation, but the testing data set when you're building the evaluator for testing. But another important point is that this allows us to also maybe potentially look at evaluating different kinds of data sets while being trained on some other data sets. So maybe I trained with skm-tea, but I want to evaluate on fastMRI. So this customizability allows us to kind of override what this evaluator would look like. So I think kind of going on top of that, we briefly mentioned kind of the importance of this config object. But really what this config is most useful for is it gives you a centralized place for setting particular parameters that can interoperate with different components in meddlr. So different components in meddlr are built to take in the config file and look for particular fields in order to instantiate that class. So you can think of it as a lazy instantiation, where once the config is passed in, the config gets parsed, and the method knows what particular parts of the config to look for. And a natural question would be is, okay, well, there's a config in meddlr, but I have some customized things that I want to do. How do I integrate these customized pieces into the config? So meddlr has a way of customizing the config as well, and kind of pushing the parameters or fields of interest to you back into the original config. And we'll see kind of how to do that here. So in a Pythonic environment, you can go ahead and get the default config, and you can set different kinds of configurations for the different parts of your experiment. So for example, in this particular kind of collab notebook, we'll be using a standard UNet model to do reconstruction. And what this will mean is that we'll kind of pass kind of the raw case or undersampled case-based data with the sensitivity maps into the UNet, and the output will be kind of the reconstructed image. And so this is a default model, as we saw earlier, that's available in meddlr. But if you have your own custom model that you've built, you can register that in the meta architecture registry, and then you can just pass the name of that class directly here. And there's different kinds of fields that are useful for instantiating this model. So for example, the number of channels that are in the input, number of channels that are in the output. So here we're separating real and imaginary into 2 channels, but it also has complex valued support. So you can use complex valued convolutions and things like that PyTorch now supports. UNet also has different number of channels at different kind of stages of the UNet architecture. And so you can specify kind of what the default kind of channel count is for the first layer, which gets kind of doubled every layer that you go down, and the number of pooling layers that you perform. So again, all of this information is used to instantiate the UNet model. And then we can also define what the loss function we want to use here is. So we wanted to use the MAE loss. And if we scroll back to our trainer, we can see that when we're building our loss computer, we're actually looking at this particular field in order to determine what the loss is. So this, again, is sorry, what was your question? So this in particular is a custom loss function that we have developed, but there's built-in kind of string maps for your particular loss function as well. So just like other parts that we can configure are the data sets that we want to use, like if we're training, validation, or testing, as well as kind of what is the retrospective undersampling that we want to do. So I'll be undersampling scans at 6x acceleration for training and also 6x for testing. And what is the calibration size that we want to use? So this determines how the Poisson disk masks are created. And then we will, one important thing I think in the deep learning space is looking at the time scale. So as Jeff mentioned, kind of units are critical. So when people talk about time, it can either be in iterations or number of steps or number of epochs, and that can change kind of how these different numbers, right, for like number of steps that you're training on or number of epochs that you're training on, what that number will actually correspond to. So here you can establish a time scale that will later be used in order to parse different kinds of fields. So like the max number of iterations, if you put 200, and the time scale's iterations will be 200 iterations. But if you change this to epoch, it will be 100 or 200 epochs that you're training for. So it's important to kind of set the time scale as you are going through this process as well. And I won't dive into too many of these details, but there's kind of a lot of work in kind of how we establish certain solvers, what are the different optimizers that we use, things like that that can all be configured in this config file. So we'll go ahead and create this config file. And as I mentioned, this is all being done in a Python environment. But really what we may be interested in is having some kind of file structure for writing this config, either in an automated way or manually writing it, and be able to kind of tune different hyperparameters and things like that. So this config is actually written out to a YAML file, which is a file format that looks like a dictionary in file syntax. And this means that you can kind of share that config and someone will know, okay, well, this was the configuration that was used for running this particular model for maybe this particular setup. And again, this is critical for reproducibility because all you really have to do is share that config file and someone can download meddlr and run that config file straight away. So now that we've created this config, we can go ahead and pass it into our skm-tea trainer class. And what we're going to do before we do all this is we're going to seed all of the different random number generators in skm-tea, or sorry, in meddlr. So things like NumPy or the built-in random package or even Torch has different random number generators, and we want to make sure that we're seeding them for reproducibility. So we'll seed them, instantiate the trainer, and we'll go ahead and start our training. And what this process looks like is it's going to compute the dataset statistics again for if it hasn't already been computed, and this gets cached on your file system. So if it's already computed, this will be very fast, and then it will go ahead and start the training. And just kind of in a standard way, it's just logging to your std out what some of your loss is, what your iteration is at that particular point, and then we've set the evaluation to occur every 50 steps or 50 iterations. And so it's running the validation kind of evaluation right now. So every 50 steps, it will run that evaluation. Kind of an important thing to note is that this is great if you're trying to kind of look at your terminal to see kind of what the loss is, but it's not a very tractable way for looking at what your loss curves look like or what kind of your validation curves look like, or even logging or looking at intermediate images at different steps in the training cycle. So there's been a lot of work externally, just generally in the deep learning community, to focus on this idea of experiment tracking or logging. And meddlr kind of is compatible with several of these different logging frameworks. So things like TensorBoard, weights and biases, comment-ml can all be used as standard loggers in meddlr. And the reason this is exciting is that you get kind of nice interfaces for looking at particular training curves as you're going through the training process. And weights and biases and TensorBoard, they also allow you to log images. And this is great because if we're doing reconstruction, we want to make sure that we're looking at our images at different stages of the training cycle, making sure that image quality is improving. because sometimes the metrics that we're using are not always kind of correlated with the quality or kind of the visual quality of interest. So this training will maybe take about a couple minutes, but we can see kind of as the validation evaluation is happening, our evaluator is spitting out what these metrics are. So it's spitting metrics out on a slice basis as well as a scan basis. There's only one scan in the validation data set. So if we're computing the standard deviation, it will be default NaN because there's only one scan. But we can see that we can get all of these metrics with ease. So the evaluator code is maybe 4 or 5 lines of code. And so you can kind of customize your own reconstruction evaluation using built-in metrics or your customized metrics as well. So kind of as this keeps on training, I think another thing that was important to mention is that the files that whenever you start training with your trainer, this automatically writes your configuration file to whatever output directory that you set. Whatever output directory that you set here. So what this does is that now you know, even when you're trying to read, run, or reproduce your own experiments, what the particular config was for the experiment that you're looking at. And so kind of my workflow around meddlr is that if I'm kind of pushing kind of a research paper or something like that, I make a list of the different experiment directories that I have that are being shown for a particular research paper, and I rerun those experiments in order to validate that the results are the same. And this is very easy to do because the config is already saved, and I just have to rerun that config on kind of a new, or just rerun that config in a new run. So again, kind of the focus of meddlr has really been how do we bring standardization and reproducibility to the forefront of a lot of the deep learning work that we do in MR reconstruction. I think this should be close to finishing. It's training for 200 steps. So I think this should be the last inference step. And once it finishes computing these metrics, it will go ahead and give us a summary of what that training run looked like. An important thing I forgot to mention when I was talking about the metrics is that the implementation of these metrics is done both on the CPU and the GPU. So all of these metrics are actually being computed on the GPU. And the reason it's slow is that the GPU that we were assigned on Colab is kind of an old GPU that makes some of these computations slow. But when we're thinking about doing things like 3D SSIM, this can be extremely slow to run on the CPU. Right? And this is the kind of SSIM that we have to run when we're doing scan-wise validation. So we're going to go ahead, because this is all kind of optimized, we've gone ahead and done that in meddlr as well. So we also output just standard CSV files that you can use for visualization purposes. And as I mentioned, you can use kind of standard experiment trackers like tensor border weights and biases. And we can also visualize these curves by just loading in that CSV file and onwards. So this is all great. We've kind of run our experiment. We've stored it. The config is stored. The weights are stored in the experiment directory that we put it in. But now what we're interested in is finding the best checkpoint. And what we might often know is that the checkpoint may differ based on the validation criteria that we're using, right? So typically we may use a validation loss. Maybe we want to optimize for validation SSIM instead. And so trying to parse through the different log files that you have or checkpoints that you have and figure out what file is best for a particular criterion can be quite tough. So meddlr has this built-in utility for finding the best weights for a particular config or experiment that you've run based on a criteria. So here the criterion we're going to use is the validation scan SSIM, and we want to maximize that because SSIM is something that should be maximized if we're finding the best set of weights. So we can go ahead and run this, and it'll kind of log out what are the best weights and what that weight path was. So as we can validate here, the validation SSIM is highest for the last checkpoint that we have, and that is the checkpoint that's returned to us. And just in standard PyTorch syntax, you can go ahead and take the model and load that weight matrix back into the model. So this is great because now we can find our weights very easily. And so let's go ahead and run this model on the test set. And just keep in mind that this model wasn't trained for a long amount of time. So you probably will get poor results when we're looking at kind of the actual images, excuse me. But what this shows is that it's a very simple kind of interface for how we can run evaluation on our test set. And we can go ahead and visualize what these images look like. So we'll just wait just a sec for this to finish. And kind of the different pieces here are, we're going to just kind of look at or batch the different targets and predictions, concatenate them together, and we're going to reformat the image in the sagittal plane. So all of the reconstructions are happening in the axial plane, but we'll see a lot of the aliasing artifacts in the sagittal plane a bit clearer. So we'll go ahead and plot these. And we can see that kind of the reference images look like this, while the predictions from our model at that particular checkpoint have these outputs. So we can still see kind of quite a bit of residual aliasing around kind of our images, but this is kind of quite useful because now we can easily visualize our images based on the models that we have trained. And it's very simple for us, as I mentioned before, to find our weights and stuff it back into our model. So now we've kind of done our intermediate validation, we've trained our model, and really I think the exciting part about this presentation is how do we share this model with different users? And it's, I think the piece here is that we don't want to reinvent the sharing platforms that exist. There's a bunch of different ways of hosting the models out there, like Hugging Face, which is one of these platforms, as well as just putting your weight or config links onto Google Drive or your website. And so meddlr doesn't take any opinion on how you choose to share your model. It just provides some utilities for preparing your model for sharing. So we have this function that prepares our model. And what we want to do is we want to put the config as well as the best set of weights for, let's say, the validation SSIM that we have into some other folder that we can go ahead and share. So that's what we're going to do here. Is it's just going to prepare our model for sharing. So it's taken the experiment directory for the trainer or the training run that we just did. It takes the model name. So what is the folder you want to save it in, as well as what are the best checkpoints, or what is the best checkpoint that we want to use. So what is the criteria that you want to use? Another really important point is that kind of it's important to put, if you can, if your model is not super large, to put your model on the CPU, because when you're sharing these models publicly, not everyone will have access to the accelerators that you use during training. So you want to make sure that this is available to anyone. And if you just pass device CPU, your model weights will automatically be moved to the CPU and saved in the folder. So when we're looking at this output directory, the skm-tea mini dummy models that gets output here, we can see that it has a config file and a model checkpoint file. And as I mentioned before, the config file is kind of a catch-all for saying this is exactly how an experiment should run, which means it also establishes how the model architecture should look. So if I just give someone a config file and the model weights file, they'll be able to kind of reconstruct the model that they want to use downstream. And this is all we rely on for sharing. So what we're going to do is we're just going to upload this model to Hugging Face. And if you want to also do this on your own, feel free to. You'll need to make a Hugging Face account. And so I'm going to go ahead and kind of look at my tokens, copy that, log in. It should authenticate me. And then I'm going to go ahead and create this repository. And so what we've found here is what we've used as Hugging Face utilities for taking the folder that we had and pushing the config and weights file onto some kind of folder on Hugging Face. And this is the URL to that folder. So we'll go ahead and navigate there. And we can see when we look at the files and versions, there's that UNet folder that we had and the config and model checkpoint files. So now these are publicly hosted. You can also privately host them if you want, but these give us links that we can now use in meddlr. So what we've done is we've kind of done the upload step right here. And we're going to kind of take the URLs for the config and weights files. And meddlr has this utility called getModelFromZoo that if you pass the URL for the config and the URL for the weights file, it will build the model for you. So from a usability standpoint, if you're uploading your models, there's very limited things that you have to do. You just have to prepare your model for upload and then upload the links wherever you see fit, and then make those links public to the folks that you want to use them. And as a user, if you'd want to use those models, it's just a one-liner to build that model again. And just to make sure that the model is working, we'll go ahead and, as kind of the original model was, we'll just go ahead and run the evaluation again and look at those sagittal reformats. And we'll see that these images look exactly like the ones we had above because the model is exactly the same. So really, again, what we wanted to do here is make model sharing a first-class citizen, because when we run our experiments, we want to be able to host our models somewhere, hopefully for other folks to be able to use them. And this is, again, there's a lot of different platforms and a lot of different ways to do this, but meddlr is not really opinionated. As long as you have the URLs for the config and the weights files, you can rebuild the model with ease. So just kind of as the final step of this demo, we'll see kind of what those images look like. And we can see we get the exact same kind of aliasing artifacts that we saw with our previous model because the model is the same. So hopefully this presentation gave you a little bit of an overview into meddlr, as well as a few utilities for the skm-tea dataset. It's important to note that meddlr also has utilities for other datasets like fast MRI for both knee and brain, as well as MRI datasets that exist for the MRI reconstruction space. And also meddlr is not limited to image reconstruction. So it has a lot of other tools for downstream image analysis, like segmentation, classification, detection, and so on. So yeah, I think that was all I want to present today, and happy to take any questions.
Thank you, Arjun. That was great. Very, very detailed and hands-on. Yeah, I'm amazed at what you put together. Let me just make you
Can I ask a question?
big as well. Yes, of course. We can start with you.
Super overview, Arjun. Thanks very much. So you have an impressive collection of about a dozen different neural network models already built into this. As you know, seems like every day or week on Archive, people are presenting new methods for image reconstruction. So is it possible for somebody, what needs to happen if you or somebody wants to add a new method to the collection?
It's a great question. So there's a couple ways of doing that. One way of going about it is kind of building it into the meddlr kind of framework. So you clone the repo, you add the model there. It's typically a torch NN module, so it's more of a copy and paste. Maybe add some of the fields for instantiating that model to the config. And that's very tightly coupled. But I think, as you mentioned in your presentation, that's not a really scalable way of adding a lot of these models, right? Oftentimes these things are decentralized, and we want to make sure that we're supporting them. So what folks can actually do, and this is actually a PR that we're working on right now, is let's say you have your own custom model and you put it on your GitHub repository for your particular project. In the config file, you'll be able to pass the link for that particular repo and that particular file, and we'll be able to fetch, like download that file, make a symlink for that file into meddlr, or a package link, and then that model will automatically be registered in meddlr. We will do all of that handling under the hood, and then the user will still be able to use that model. So I think this may help with things like kind of rapid kind of innovation, as you were saying, right? There's going to be a bunch of models that people will be putting out. But hopefully it'll also kind of create a little bit of stake of how we can still have a decentralized space of these models, but really build the right connections to have people be able to use them in a cohesive way.
Cool. Sounds like that would really facilitate comparisons of different methods. Thanks a lot.
Yeah, thanks.
Yeah, let's carry on with a question that I have, which is basically the same that Niku asked Jeff and Toby in the first part. It's what has been the most challenging part of developing a toolbox, getting it out there? And like, when you say we, how large is your team? How large of well, yeah, how many people are working on meddlr with you?
Yeah, so it's definitely been kind of a long process. A lot of it was also just like becoming familiar with like great open sourcing practices and some of those pieces. The team is right now, or like the core team is still quite small, but we are pretty excited to get a lot of kind of additions from several other users. So I think we're working with a lot of folks to kind of get their models onboarded in meddlr, and even at minimum use kind of the sharing framework in order to be able to distribute their models at scale. I think kind of the most difficult piece is really the infrastructure, I would say, is that how do you build the code in a way that is flexible, but also optimized for particular operations. And I think in Python, there is a lot of boilerplate that often has to get written, but you need to often go to the bottom of that boilerplate, look at a lot of the low-level operations, and really optimize things at maybe an array level that in order to really get the speed up that you're looking for kind of in a lot of these deep learning frameworks. So that definitely was pretty exciting dive to take, but definitely quite time consuming.
Yeah, I can imagine. Kind of building on from that then, and kind of taking a step back, looking at MR research at large, do you think there is a need for more people that are specialized in software engineering, and how can we support those kind of people within academia?
Yeah, I think I'm definitely a very biased and strong proponent for software engineering in any discipline. I think it really just simplifies how we're able to share the tools that we build. I think MR is definitely very ripe for a group of software engineers or just software engineers like being part of the stakeholders that are in our community. But there are a lot of them already there, right? So I think a lot of the folks that have been like Jeff and Tobias, as well as many of the folks that presented earlier in MRI together, they've really done a great job of kind of pushing towards good open source practices and building things into the MRI community. I think having kind of dedicated software engineers is always very useful because that's like kind of their primary role, and maybe kind of the support that they can give to a lot of these projects is more extensive than maybe we can give at any point in time. But I think that's just kind of how the community can evolve, and it'd be really exciting to see how we can get or incentivize kind of software engineers to tackle the right problems that we have in MR.
Yeah, thank you very much. I don't see any other questions in the chat or in the Q&A at the moment. So yeah, if there isn't anything else, I think we're fine rounding up this session here. Thank you very much to all of our speakers. Yeah, I'll bring you down here to the main stage as well, so we can have us all together, say goodbye. But yeah, it's been a very enjoyable session. Thank you all for presenting, and to all of the attendees and speakers as well. If you want to know more or discuss with people, GatherTown is going to stay open. Make sure you go and check out the posters from our community abstracts that people have submitted to us. There's some really, really impressive work there as well. But yeah, with that, let's end MRI together for this year, and hope to see you all again in a year's time.
Thank you.
Thanks.